Hi everyone, welcome to the first presentation from the Equine Podiatry Shed, Pull and Vale. Look forward to more presentations of some of our more interesting clinical cases in coming months. Why look at hoof microanatomy? Unfortunately, around 67% of lameness issues arise from hoof pathology of some form. Many hoof issues can be extremely painful and can be serious welfare or even life-threatening issues. The key to managing virtually all cases requiring remedial shoeing is to increase hoof and sole growth rates. Regrowing the hoof wall in acute traumatic circumstances such as this is critical from a welfare perspective and for reducing return to work timeframes. Whether it be an acute or chronic rotational laminitic condition such as this, where incremental wall and sole growth will help protect P3, enabling earlier response to remedial shoeing, or in a type 4 P3 fracture such as this, it's essential we have accelerated sole and wall growth for support and fracture resolution. Bone sequestry such as this fracture secondary to a penetrating injury, sole and hoof growth were critical in this case's management, as was regenerative capacity post-infection in this case, where we needed to regrow sole as quickly as possible. Hoof capsule cracks are a classic example. Whether they're dorsal wall or quarter cracks such as this, they can be career-ending unless managed correctly. Accelerated hoof wall growth not only inherently grows cracks out faster, but increases available hoof mass, giving the farrier more to work with, enabling faster return to work. Post-osteomyelitis or post-operative cases like this, where we had extreme lysis of P3, are perfect examples of where elevated hoof wall growth was essential. Here we had a navicular fracture with clear resolution change in 4.5 months. The horse was sound and back in work, well inside the globally recognised expected healing timeframes. Elevated hoof wall growth rates greatly assisted in the outcome. Increasing hoof wall and sole growth is inherently linked to successful remedial shoeing outcomes, and at the end of the day, helps horses' welfare. So let's dive into some anatomy and get to an understanding of how the hoof wall, sole, and frog are produced. Here we can see a postmortem specimen with the hoof capsule removed, and immediately we can identify these fine velvet filamentous projections running all over the sole and frog. These are the papillae of the sole and frog, and along with the coronary papillae are structures which produce the keratinized hoof capsule. This diagrammatic representation of a cutaway of the hoof wall shows the coronary papillae. Coronary papillae are responsible for producing the actual hoof wall. The hoof wall is only produced here at the coronary band and slides down the secondary germinal epidermal lamellae of the hoof. Now we could start to talk about laminitis, however you'll just need to wait until one of our next lectures. Just to reiterate, the hoof wall is produced at the coronary and slides down the lamellae. No wall is produced by the lamellae. Here we have a magnified view of the coronary papillae and the sensitive lamellae with the coronary groove over here with these holes, which are the origin of the tubules, and then we have the insensitive laminae. Although this appears so unusual, almost like an anemone, these are actually sole papillae here, and we have the corresponding tubules of the sole here. You can imagine how easily these papillae can be bruised or damaged, and how complex, for instance, drainage of a simple hoof abscess can be. Now we have to ask why papillae? Why not sheet keratin laid down from a nail bed like the human fingernail or toenail? How do the papillae produce a keratin structure utilizing almost exactly the same sort of cellular building blocks as a human fingernail to overcome the weight, torsion, and impact required of a horse at the gallop of approximately 5 to 6,000 pounds per square inch? To put into context, at 5 to 6,000 psi, we have nearly double the psi of a saltwater crocodile's bite force. Suddenly, the functional papillae mechanism seems to become intriguing and makes a lot of sense. Essentially, the papillae are concentric cones of decreasing radius separated by flatter areas of basement membrane, which produce the intertubular matrix. We can see now the concentric epithelial rings of the papillae now producing the rings of the keratinized tubule separated by the intertubular matrix. This is a highly oversimplified version of how keratin is produced from the basement membrane. Down here, utilizing a human diagrammatic skin model, the cells are not producing keratin. They are progressively produced, die, shrink, and inspissate to become mature keratinized hoof. They are highly complex bonds that then bind these mature keratinocytes to each other. This is a different author's diagrammatic version of the multi-layered tubules and the intertubular matrix being the flexible glue holding the tubules together. More recent research has shown that each layer here actually spirals in the opposite direction, yet again enhancing the torsional strength. This is an incredible electron microscope picture of an actual tubule showing the compound cylindrical layers surrounding the intertubular matrix by Benjamin Lazarus in 2022 from the University of California. As in so many cases in nature, engineers have copied and extrapolated the compound layered cylindrical concept with rocket motor cases, submarine hulls, pressure vessels, aerospace vehicles, and power drive shafts. This is a nice graduated cross-sectional view from the outer hoof wall through to the inner hoof wall with an electron microscopy overlay. Here we can see the differing tubule density between the outer and the inner walls, which aids in the viscoelastic properties of the hoof capsule. Okay, so we've established the hoof wall as a keratin-based compound, multi-layered tubular structure bound by intertubular keratin matrix. What does a keratin molecule look like? How is it structured and how does it function? $64 million question is obviously then how do we increase keratinocyte and then healthy keratin production and hence hoof wall strength? Most keratin supplements are ground up cattle or sheep hoofs, such as this one. The problem is horses can't absorb keratin or collagen. These are complex, large polypeptide sequences that need to be broken down to be absorbed. Let's have a look at a diagrammatic representation of the keratin polypeptide double helix and the bonds involved in holding the two polypeptide chains together. There are three types of bonds holding the chains together: a hydrogen bond, an ionic bond, and a disulfide bridge. When we flatten out the polypeptide chains, we can see the difference in each of the bonds, the strongest of which is the disulfide link. Here, clearly a complete biochemical bond. The hydrogen and ionic bridges assist with the polypeptide strength. However, the key is this disulfide bridge between the two essential amino acid molecules of cysteine. We can also see on the flattened version we have these repetitive structures with a double bonded oxygen atom. Each oxygen atom, here, each oxygen atom is a part of an amino acid which makes up the keratin polypeptide chain. There are four primary amino acids in a keratin polypeptide. This is a 3D model of a cysteine amino acid molecule. Cysteine is the only non-essential amino acid found in keratin, however, holds particular significance due to its unique thiol or sulfur functional group here in yellow. Here we have arginine. Arginine is an essential equine amino acid. Now, what's the definition of essential amino acid? It's an amino acid that cannot be synthesized from scratch by the organism fast enough to supply its demand and must therefore come from the diet. Lysine, also an essential equine amino acid, and methionine, the final essential amino acid required. Quite simply, without these four amino acids, a keratin polypeptide cannot be formed. Therefore, keratin cannot be formed. This cysteine structural formula diagram shows the disulfide bridge here joining the two cysteine residues. The disulfide bond is responsible for the mechanical stability and tensile strength of hoof wall. The bridge is the most powerful naturally occurring bond in nature, and consequently cysteine needs to be fed in sufficiently high enough doses to be incorporated into a keratin polypeptide. So what are the factors that can affect this polypeptide that influence and enhance hoof wall and sole quality? The Canadian Veterinary Research Journal produced an interesting paper describing the factors affecting hoof wall quality being nutrition, hydration, genetics, foaling, now environmental factors such as chemical agents and underlying coexisting pathology. We can see the frayed toothbrush effect here around the peripheral weight-bearing circumference of the hoof. This is a perfect example of where the keratin strands at a molecular level are unraveling as ammonia cleaves the disulfide bridge of the double helix polypeptide, causing the intertubular matrix and tubule structures to simply fall apart. The Journal of Anatomy in 2009 published a fantastic paper where soaking hoof wall in urea and fecal slurries had an absolute direct correlation with hoof wall degradation. Strength was found to be reduced by more than 50% after 48 hours of soaking. The significance of the findings is highly practical. A strong ammonia smell in any stables can now be related directly to hoof health and potential degradation rates. This is a great study done by Hong Kong Polytech on how hydration can affect a human hair after 24 hours of soaking in water. Extrapolating the loss of integrity of the core of the shaft gives an insight, and you can see the core of the shaft here just swelling and falling apart. Insight into how water can influence the structural integrity. Already we can see microfractures appearing longitudinally down the outside, very similar to what we see with horses standing in wet paddocks for extended periods. In this study done in 1987, we see here RH, which is relative humidity, and E, which is tensile strength, here and here. We resulted at 100% saturation versus 0% moisture, resulted in a decrease in tensile strength by a factor of 35. Incredibly significant from a practical perspective. So where do we begin with conceptualizing a formulation? We realize we need to incorporate the fundamental requirements from a chemical perspective of keratin. But what other ingredients could assist in hoof wall growth and strength? Although this is or was a Tesla, basically we reverse engineered hoof wall to a molecular level, ensured we supplied all of the building blocks we could possibly include, including some compounds which have been shown to assist in keratinocyte replication rates. We also looked into actual clinical research on the validity of biotin as an effective supplement due to the amount of public interest in vitamin H. The only genuine standalone trial we could come across was conducted in 1995, which showed no difference between placebo and trial groups. At this point in time, there are still no peer-reviewed clinical papers published with evidence that biotin stimulates hoof growth, so it's possibly one of the world's greatest equine myths. Having said that, despite the potential mythology, we sourced human pharmaceutical-grade biotin and combined it with cofactors to dramatically increase absorption bioavailability in hoof gold. Part of our research accidentally uncovered the breakdown of keratin, including heating and burning. So for those hot shoeing, what are the byproducts of keratin burning? Unfortunately, one of the byproducts is H2S, dihydrogen sulfide, commonly known as mustard gas. It goes without saying, has had a bad history. The bottom line is, get a fan, something with some grunt, well worthwhile, just for your own protection. Once we developed our formula, our initial hoof gold clinical trials were performed in an equine veterinary spelling facility in Victoria. Trials and interpretation of results were all performed by veterinarians and reviewed by a specialist independent equine veterinary radiologist. This particular horse, one of many in our large trial groups, was a Godolphin horse with a 6-month paddock spell. Standard diet, no change to any part of the normal spelling diet. A thin piece of lead was inserted in a groove, 23 millimeters here, distal to the coronary band in the dorsal hoof wall, then glued with a high shore hardness polyurethane. This enables us to accurately measure coronary distance to 1/100th of a millimeter. In the 30-day control period from days 0 to 30, no changes in diet or environment were made. The wall grew from 23.13 millimeters to 26.17 millimeters. So we had a 3.04 millimeter growth in 30 days, 3.04 millimeter growth. From day 30 to 60, 2 scoops of hoof gold were fed once per day in addition to the moistened standard feed. Growth radiographically recorded from day 30 to 60 from 26.17 to 39.75. This equates to a 13.58 millimeter per 30 day versus the 3.04. So just to repeat that, 13.58 versus 3.04 for the same period. This translates into a statistically high significance in incremental change to hoof wall growth. It equated actually to a 447% increase compared to the previous non-supplemented wall growth in an equivalent period. Quite a remarkable result. Cases like this, we recommend using hoof gold. These are cases where we're just interested in accelerating hoof growth. However, when we need to assist with bone reparation and hoof wall damage, we move to bone gold. Bone gold is simply our next generation formula that successfully manages both hoof and bone growth. Here's a classic case where we had a surgical dorsal wall resection. Post-osteomyelitis, and 5 months later, we can see radiographically the bone is stable with no secondary arthritic or sclerotic changes, and the hoof wall is totally regrown. This was a post-surgical keratoma case showing great wall growth in 11 weeks, combined stability of the pedal margin radiographically. Radiographs measured dorsal wall growth 13.14 millimeters per 30 days versus, again, the 3.04 millimeters per 30 days we expect and we saw in our trial group. When we have P3 lysis in keratomas or osteomyelitis, the solar margin damage never seems to recover. We see over a period of 12 months normally a resorption process where the bone rounds off. Here we can clearly identify increased bone density and trabecular formation post-surgery. As far as we're aware, this is the first documented solar margin resolution of lysis secondary to surgical keratoma removal. You can see here we have a 32 millimeter by 4 millimeter type 4 P3 fracture and 12 weeks post-injury. We come across a lot of these. They present with diffuse intermittent solar margin pain and are often undiagnosed. These fractures are a common cause of poor performance in racing. Type 4 fractures have an anticipated 9 to 12 months expected recovery period. However, in this case and multiple other cases, we were able to return the horse to work at 12 weeks. Thank you, and I hope you enjoyed our first presentation. We're going to work our way through some interesting clinical cases, so please watch out for our next one.